When a furnace is running, operating conditions have to be carefully monitored and controlled. Operators need to keep an eye on process variables and other conditions and make adjustments to keep the furnace operating at peak. During furnace operation, you'll rely on a variety of instruments to give you the readings you need. Furnace conditions are normally monitored from a control room and from instrument panels at the furnace. One condition that must be monitored and controlled is airflow. Process variables relating to airflow include draft and excess air. Draft is the flow of air and other gases through a furnace, and excess air is the amount of air supplied to the furnace in excess of the theoretical minimum amount required for combustion. A furnace won't perform efficiently if the draft and excess air are off. Draft is often determined by measuring pressure at different spots in the furnace. In this case, there are pressure transmitters that measure draft at the top or arch of the radiant section and at the base of the radiant section, in the firebox, that is, in the area where combustion occurs. Draft may also be measured in the stack, typically at a point below the stack damper. Draft is usually measured in inches of water, and the draft gauge reading should be correct for all of the areas in the furnace. If the draft is positive when it should be negative, the furnace won't perform well, and there's a risk of damage to the furnace structure. Now, excess air readings are based on analysis of the flue gas. In general, this analysis determines the percentage of oxygen in the flue gas, and that percentage gives an indication of excess air. Furnaces normally have draft and excess air targets or acceptable ranges. Operating within the targets can save money in fuel costs. Basically, the airflow conditions in a furnace are controlled by coordinating the positions of the stack damper and the burner air registers. In addition to the airflow conditions, the fuel supply to the burners also has to be controlled. If there's too much fuel, some could be wasted because fuel may leave the furnace without being burned. If there's too little fuel, there's a risk of flameouts and explosions. The pressure needed for proper fuel flow is regulated by control valves. These are the main fuel control valves. They regulate the overall fuel system pressure. In this system, fuel flow to the header is regulated by this control valve, which is called the fireman. Since flow depends on pressure, the fuel pressure is measured. Pressure is typically measured in units of pounds per square inch. In this case, it's pounds per square inch gauge, PSIG. When fuel is burned, it produces flue gases. A process variable that's closely watched is the flue gas temperature. Flue gas and other furnace temperatures are usually measured with thermocouples. Flue gas temperature is often measured in the convection section and in the stack. If the flue gas temperature is too high, there could be a fire in the convection section, or the furnace may be operating above the normal firing rate. An excessive firebox temperature can overheat the tubes and refractory and damage tube supports. So far, we've seen furnace instrumentation related to fuel supply and air supply. Now we're going to look at the process. Two main variables associated with the process fluid system are temperature and flow. The outlet temperature, in a sense, is the most important furnace temperature reading, since the main function of the furnace is to heat the process fluid to a certain temperature. Another temperature that's routinely checked is the tube metal temperature, or skin temperature. Overheated tubes can lead to tube ruptures and other problems. Besides temperature, the process fluid flow rate is also monitored. The fluid has to flow at the proper rate to be heated to the proper temperature. The flow rate for process liquids is often measured in barrels per hour. For many furnaces, both the process fluid outlet temperature and the process fluid flow rate are controlled automatically. You should know how your furnace's control systems work so you can monitor the way they're controlling the furnace. Let's look at a typical example. This system controls the process fluid outlet temperature by adjusting fuel flow to the burners. There's a thermocouple to measure the outlet temperature, a temperature controller, and a fuel flow control valve. During operation, there's a desired outlet temperature or set point. Deviations from set point trigger control actions. For example, if the outlet temperature gets too low, the temperature controller picks up the change and signals the fuel flow control valve to increase fuel flow to the burners. The additional fuel generates more heat, which brings the outlet temperature back to set point. Now, if the outlet temperature is too high, the temperature controller closes the fuel control valve slightly. The valve allows less fuel to flow to the burners, which causes the outlet temperature to drop back to where it should be. For some furnaces, the flow rate of the process fluid is also controlled automatically. These control valves regulate the flow in a 4-pass furnace. Each valve controls 1 pass. There's a set point for each pass. Usually it's the same for each pass. Maintaining the same flow rate allows the process fluid to be heated to the proper temperature more efficiently. If the flow rate deviates from set point in any pass, the control valve for that pass is repositioned automatically to increase or decrease flow and return the flow rate to set point. In this topic, we looked at furnace instrumentation, process variables, and control systems. Now's an experienced operator can tell a lot about how a furnace is running by simply looking and listening. During your inspection, it's a good idea to check places where air may leak into the furnace. Air leaks can reduce the efficiency of the furnace and give misleading draft and excess air readings. The inside of the furnace should be looked at too, but follow the necessary safety guidelines. To avoid getting burned, wear a face shield and stand to one side when you open the peephole doors. Inside, the firebox should be relatively clear. If it's extremely hazy, you may not be supplying enough air to the burners. Also look at the condition of the tubes. Bulges in the tubes are warning signs of overheating, and the bulges could lead to tube ruptures. If you notice shiny or bright and glowing sections or silver streaks, these could be indications of hot spots, which are overheated areas of a tube. Also see that tube supports and hangers are not bent or broken. Damaged tube supports can be a sign of overheating and metal stress in the furnace. Look at the refractory too. Its color should be uniform. Glowing areas may mean that some sections of the furnace are getting more heat than others, but dark spots may be an indication of an air leak. What you want is a good heat balance in the firebox. When you inspect the furnace, it's especially important to check the condition of the burners and the flames. Make sure that all burners that are supposed to be operating are doing so. Flameouts invite explosions because unburned fuel can collect in the furnace. Adjusting the burners is a part of furnace operation that gives you direct control of combustion efficiency. Burners may have to be adjusted for any of several reasons. Poor flame patterns, changes in the firing rate or in the type of fuel burned, or even abrupt wind changes are a few examples. Judging a burner's performance can be tricky, but there are some basic guidelines that can help you determine if adjustments are necessary and how to make them. For example, all the burner flames should be about the same size, and the flame should be fairly still, not jumping around. An erratic, sparky flame may be the result of an improper fuel and air mixture, in which case you could adjust the air registers or the fuel flow to the burners. A sparky flame can also be caused by dirty, plugged, or eroded burner tips that need cleaning or replacement. Also, the flame should not be so long that it's impinging on the tubes. Sometimes you can shorten a flame by adjusting the amount of air fed to the burner. The fuel supply can also be regulated to adjust the flame length and pattern. For example, if the fuel pressure is incorrect, the flame could be lifted off the burner, risking tube impingement. An abnormally high fuel pressure could lift the flame off the burner. Therefore, decreasing the fuel pressure corrects the problem and brings the flame back toward the burner. If the fuel pressure is too low, the flame could burn inside the burner tips, producing a whistling sound. Most of the flame patterns and burner adjustments we've seen are for gas burners. Oil burners are operated a little differently. With an oil burner, besides adjusting airflow, another way to manipulate the flame pattern is to adjust the atomizing steam flow. For example, by adjusting the steam flow to the atomizer, you can adjust the length of the flame. The fuel oil pressure to the burner can also be adjusted. If the fuel pressure is too high for the amount of atomizing steam and combustion air that's supplied, the result could be unburned fuel oil. This shows up as a smoky, hazy firebox and smoke coming from the stack. This problem is typically corrected by decreasing fuel oil pressure or increasing steam or air to the atomizer. In this topic, we saw how to inspect a furnace and adjust the burners.